Hello everyone, welcome to video 4.2 on traveling waves. As usual, our first slide is on the data booklet reference, so make sure you have your formula booklet in front of you. Let's quickly go to that. Okay, so today we're looking in box 4.2, traveling waves, and there is that one formula in there. C is equal to F, and then some funky looking symbol there, which we will learn to be called lambda. So we'll go over that. Back to the slides. Okay, traveling waves. So as is the title of this section, we are doing traveling waves here. In 4.5, the next section, we will be talking about standing waves. So today in this section, it's where the waves are in motion. The other one, the waves will be moving, but also stationary. Okay, so the first thing we're going to consider is a taut rope, which is anchored securely to a table. Now, taut just means it's tight, it's stiff, it's secure. And on the other hand, we grab the rope, we grab the free end, and we send a single wave pulse through the medium. So we just move our hand up and down exactly once. Now, usually at the end, the wave will reflect. We're not showing the reflection here. We're just going to show it getting absorbed. Now, if you keep moving your hand up and down and repeat the motion, you can create a continuous pattern. You can create a wave. Okay, so one single up and down movement is a pulse. Continuous movement is a wave. Now, what's really important to note, and we're going to talk about this again and again throughout the section, is that the rope is not moving from left to right. The wave is moving from left to right. The actual individual matter particles in the rope are simply moving up and down about an equilibrium position. The equilibrium position being right here in the middle. It just oscillates up and down. So notice again for this type of wave, the wave traveled from left to right, but the individual particle oscillations were perpendicular to that, up and down. Okay, now we don't always have to use a rope. We can also use a spring. So if any of you played with a slinky when you were kids and ever sent the slinky down the stairs, you would have seen that it was a continuous pattern of compressions and stretches that allowed the slinky to move. Okay, so we're going to be using something like a slinky. Okay, it's a giant spring, but instead of that, imagine you have one end of the spring attached to a wall, and the other end, well, you're going to be holding in your hand. Okay, so you take that spring and you send a compression through it. So what that means is you push forward in the direction that the spring is held at that moment, and then you pull back really fast. Okay, so what that does is it sends through a compression wave that travels through the entire spring. Now, something to note is that that compression, symbolized by that dark black region, it's the compression that's moving through. It's not the actual spring that's moving from left to right, just like with the rope. Now, we can keep that up, and those compressions can keep moving forward, and then they can reflect and go backward. And once again, the spring is not itself moving. The individual particles are moving locally. Now, what's different with this example compared to the previous one is that with the rope, our vibrations were perpendicular to the direction of wave travel, up and down. Here, the wave is still going from left to right initially, but the individual particles are oscillating left and right as well. So the individual particle oscillations are parallel to the direction of wave velocity. As we'll see in some later slides, there are special names for these two types of waves. Okay, now what's the point of a wave? I mean, why are we studying waves? Well, whether it's sound waves or light waves, as we'll see in grade 12 and a little bit in grade 11, or matter waves, waves transfer energy. I mean, that is their primary purpose. Okay, so consider again that rope securely anchored to a table, except now we have an object on top of it. If we decide to send a pulse down that rope, that pulse will impart work. It'll give an energy transfer to that block, allowing it to gain height and jump on top of the table. So we're giving it gravitational potential energy. Okay, so in other words, the rope does work on the mass. Okay, now we know the amount of energy and the amount of work done. Okay, so its gravitational potential energy is mg delta h, or just mgh. So the height we can calculate based on this picture. The mass of the block would be known, and g, that's the acceleration due to gravity, 9.81. Okay. All right, finally we enter these the first set of terminology, transverse and longitudinal waves. So the rope and the spring we saw were examples of traveling waves. But the big difference was that with the rope, like I said, the particle vibrations were perpendicular to the direction of wave travel. Whereas for the longitudinal wave, well, actually, we'll get to that. With the spring, the particle vibrations were parallel to the direction of wave velocity. So what's important is a couple of things. What type of wave you have, so whether it be transverse or longitudinal, and what type of medium that the wave propagates in. So when we say medium, we mean the type of material. Okay, so waves can travel through steel, they can travel through air, they can travel through water. Okay, sound waves especially are very interesting when it comes to traveling in these different types of media. Sound actually, believe it or not, travels fastest in denser media. Okay, so I have a hypothetical thought experiment for you to think about while you're sitting there listening to this video. Okay, so don't at any time try this. Of course, it's dangerous, but it's a thought experiment. If you were standing outside near a railroad track and you wanted to hear when the train was coming, the fastest way to actually tell when the train is coming would be to put your ear on the steel track. Why? Because the only alternative would be to stand up and hear the sound of the train siren or on the rail through the air. Now, because sound, as you'll see later on in this video, sound is a longitudinal wave, and sound will travel faster in denser media. Hence, the steel railroad track would allow you to hear the train faster than if you were listening for it in air. Okay, now, here's where these definitions that I keep bringing up, the parallel, the perpendicular motions of the particles relative to the wave velocity, they come into play for the definitions. Okay, so with the rope again, the oscillation, right, so the individual particle motions were perpendicular to the direction of the wave velocity, which was from left to right. Right, I mean, we can even see how the hand is moving. This is telling us the direction that the particle is moving. Okay, so we can clearly see that that's perpendicular. When the particle motion is perpendicular to the direction of the wave velocity, we have what's called a transverse wave. Okay. Now, with the spring, we saw that when we applied a compression in the direction of the spring, a compression went through the spring and, well, it would also reflect back. But the idea was that the compression traveled along the direction of the wave velocity. And the fact that it traveled along it on the way there and backward on the way back shows that it was traveling parallel to the direction of wave velocity. Okay, so this is what's called a longitudinal wave, when the particle just oscillates back and forth about some equilibrium position. So when you look at this little red dot, whether it's in this picture or the previous slide for the transverse wave, it's really showing the same thing. I mean, this is an individual atom. It's oscillating back and forth. And no matter what atom you pick, in any part of the spring or the rope, they're oscillating back and forth about some middle point, giving the illusion and really the effect of compressions and rarefactions, or as in the other case, what we're going to call later crests and troughs, so peaks and valleys. All right, categorize a water wave as transverse or as longitudinal. If you've ever gone fishing, and specifically if you've ever gone fishing on a boat, well, you would know the answer to this. When you throw a fishing line in the water, fishing line is very, very thin and it's very difficult to see. So if you are actually throwing your fishing line into the water, you can easily lose sight of it, which is why many fishermen use something called a bobber. So it's a little very low density, lightweight, spherical object that will attach to the fishing line and it just floats on top of the water. So that way you know at any point in time where your rope or where your fishing line is in the water. All right, so it looks something like this. Now, what's on the end of that bob or at the end of that fishing line? Your bait, right? So let's say you've got some kind of a worm. Now, as the waves move from this screen from right to left, you saw that the bob simply moved up and down with the wave. Okay, so if it's just moving up and down, this would be the individual particle. That's the, I guess, symbolism here. This is the individual particle, but the wave is moving from right to left, perpendicular to the direction of the bob motion. Hence, this has to be a transverse wave. Now, another example of this would be, well, if you're in a wave pool. So sometimes in the summertime, if you go to a nice water park, they have a very large pool with a lot of water and a lot of people, and every so often the buzzer will go off, and there we have a fish. every so often the buzzer will go off and giant waves will be sent through the pool, hence the term wave pool. Now, when the waves go through, you yourself, imagine you and all the other people in the pool are the particles. You simply go up and down. You don't actually move from the beginning of the pool to the end of the pool. Well, unless you can't hold your footing very well. But it's the same idea. All right, sound waves. Now, sound waves are longitudinal waves. So the compressions and the stretches, and we'll have a better name for the stretches, but these compressions and stretches are parallel to the direction of wave velocity. All right, now, if you've ever looked at a speaker while it's playing music, so this wouldn't work with your cell phone, but if you have a nice speaker system either in your car or you have it in your home or in your friend's home, if you ever look at the speaker, you can often see the folds moving back and forth. And depending on the type of music, it might be moving back and forth a lot, and it might be moving back and forth very quickly. Now, depending on how it moves, that's what type of music it's going to create. And the way it moves back and forth is simply by using an electrical input. Now, when it moves forward, it compresses the air particles in front of it. That's what we call it compression. Now, as it moves back, we don't say that it causes a stretch in the particles, although that is kind of what's happening. We say that it causes a rarefaction. All right, so compression and rarefaction. We want to move away from using the word stretch, and instead we're going to say rarefaction. Okay, so look at this diagram here below. We're going to see the full animation shortly, but on the right here you can see there's some kind of a source. Imagine that's a speaker. Now, before the speaker actually turns on, imagine all these little dots. They're just air particles within the room, and they're all originally evenly spaced out, more or less. Once the speaker starts moving, and once that electrical input goes in and creates sound energy, this speaker is going to oscillate back and forth. It's going to move forward and backward. And notice when it moves forward, it bunches up the particles very close to it, and when it moves backward, the particles get a bit more spaced out. Now, you might have to keep looking at this for a while until you really see it. But watch as the compression moves through the entire line, right? So when it creates a compression, you can actually follow it. But it's not as if there's a particle here in the front that ends up all the way on the left side at some later point. Every single particle just oscillates back and forth. So pick any particle. Let's look at this one right here. It's simply oscillating back and forth about some equilibrium point, but it makes it look like it's moving. So the wave transfers the sound energy from right to left, but the particles simply oscillate parallel to the direction of the wave. Now, wherever the particles bunch up, we call those regions of compression. And wherever the particles, separate, we call those regions of rarefaction. Okay, so now we can clearly see that sound is a longitudinal wave. Okay, so here it is based on the picture. Regions of compression in the red and regions of rarefaction in the green. And of course, those alternate. All right, so this would be a microscopic view of what a sound pulse would look like. Okay, the idea is, okay, so you've got your pulse generator here on the left. It creates energy. It transfers energy to the line of particles immediately next to it. These particles then transfer the energy to the line immediately next to them. Then this line immediately transfers the energy to the line next to them, and so on until the energy transfers all the way through to the end. So, something like this. Okay, so you can see there's regions of compression followed by regions of rarefaction where they're spread apart. But really, this is a wave. Right? So as the wave moved from left to right, the particles also oscillated in the parallel direction. So from left to right and then back from right to left. Okay, so now as the pulse moves through the medium, there is some velocity to that wave. Like I mentioned earlier, sound being a wave travels faster in steel than it does in air. The denser the particle or the medium, the faster the transmission of sound will travel. Now that's not true for light. Light behaves actually very, very differently. We'll learn all about how light works in grade 12. We will touch upon it very little in today's video, but we'll leave most of it for grade 12. Okay, suppose the distance from the generator to the barrier is 5 meters and the pulse took 22 seconds to reach it. Okay, so then we can figure out the speed. If there is no acceleration, speed is equal to distance over time. So the distance being 5 meters and the time being 22 seconds. So we have 0.23 meters per second. All right, I really like this slide, and even after I explain it, you might want to just pause the video, go back, play it again. You can even mute it if you want, if you're just trying to look at it and try to figure out what's going on and understand the animation. Okay, so what we have here is a very unique speaker. Okay, so the speaker's in the middle, and what it's doing is it's actually oscillating vertically and then horizontally, and it's oscillating between its oscillations. So it's alternating between vertical oscillation and horizontal, vertical and then horizontal. So that's kind of a wave pattern in and of itself, but we're not going to get into that. What I want you to notice is whenever this speaker pushes outward, okay, whenever it pushes outward, those particles get squished. And then when it pushes outward in the opposite direction, horizontally, let's say, then you have what's called a rarefaction. So compression followed by a rarefaction. Now, whenever the particles are getting compressed vertically, they are getting stretched or rarefacted horizontally. And so what we're going to notice is that the wave, or the parts of the wave in the red sectors, are what we call out of phase with the waves in the blue sectors. Okay, so here are the red sectors. This is the horizontal part. Here is the vertical part in the blue. Okay, so just pick any point. I mean, you can see the compressions and rarefactions keep moving, but just pick a point. Okay, watch the compression move through the wave. Okay, and then try to see exactly what's happening in the blue part. And if you look really carefully, you'll notice that when there is a compression in the red region, there is simultaneously a rarefaction in the blue region, or vice versa. So those two parts are out of phase by half a full cycle. Okay, now I keep using this this terminology. What does it mean to have something out of phase? Okay, well, if two things are in phase, specifically we use this terminology when talking about waves. If two waves are in phase, that means that their peaks and their valleys are lined up. Okay, or in this case, the compressions are lined up and the decompressions are lined up, or the rarefactions. Okay, so here, because we have a compression exactly lined up with a rarefaction, they are exactly half of a cycle out of phase. This will make a lot more sense once we investigate what it means to have a full wavelength and what comprises a full wavelength and what it means to have something half out of phase, a quarter out of phase, fully out of phase, or in phase. All right, wave fronts and rays. So we've got a snapshot of that animation, and we're going to be looking at something. Now, a wave front is simply a piece of terminology that's going to continue into our studies in grade 12. So it's important that we introduce it now. A wave front is sometimes regarded as the beginning of a wave. And so arbitrarily, physicists just said, well, let's just let the wave front be wherever the compressions are. Okay, so for a longitudinal wave, the wave fronts are where the compressions are. So you can see that in the two different directions in the red and blue lines. If you have a transverse wave, wavefront is defined as the location of a crest. Now, what is a ray? A ray is simply a vector that tells us the direction that a wave is traveling. So with the blue waves, you can see that they're moving outwards up or outwards down if you're looking at the bottom half. For the red, they're either moving left or right. And what we're going to notice is that rays, we always draw perpendicular to the wavefront, so always at 90-degree angles. All right, let's compare the waves traveling through the mediums of rope and spring. Okay, so we've got a transverse wave here, and we've got a longitudinal wave with the spring. Now, when you have a transverse wave, the peaks, or the points that are high, we call these crests, and the points that are lower, the valleys, we call those troughs. Now, I know it's spelled tro, but you pronounce it trough. Okay, almost as if it was spelled T-R-O-F-F, but it's not. Okay, so you just have to remember that. Now, with longitudinal waves, we don't have crests and troughs, but we have regions of compression and rarefaction. So while a crest and a compression are not the same thing, they are similar. And a trough and a rarefaction are not the same thing, but they are similar, hence why they're color-coded in this way. All right, now this is a nice animation because it shows the movement of a wave, but it also shows the movement of the individual particles in the wave to help you get a better sense of, well, what it really means when you have a transverse wave. Now, in this little bullet point here, it says the medium is in simple harmonic motion. All of that means, those three words are actually pretty important. We're going to see it later on and in grade 12 as well. But simple harmonic motion simply means that you have an object that is oscillating back and forth about some equilibrium point. Okay, so whether that's a child on a swing swinging forward and back about that middle point, or whether it's a pendulum that's swinging left and right, or perhaps it's a mass on a spring oscillating up and down or forward and backward. All of these are examples of simple harmonic motion. Okay, so we've started our timer and the wave is in motion. Now notice if you just pay attention to the particles, all they're doing is moving up and down. Once they move down, they go back up. Once they hit the top, they come back down. Pretty simple, right? But then if you stand back and look at the big picture, what you really have is a wave. Okay, so what you should do is notice a couple of things. Each particle has the same period. Okay, let's talk about that. That's a new word. Period is the length of time required for a wave to complete one full cycle. I'll say that again because it's not in your slides. A period, and it's symbolized by the letter capital T, well, period is a length of time, and since time we represent with lowercase t, we always use capital T for period. Now, period is measured in seconds, but period is, again, the length of time it takes for a wave to complete one full cycle. Okay, so that's what it means. Now, how do we know they all have the same period? Well, if you look at each particle takes the same amount of time to go from the top to the bottom and back to the top. Okay, so that's one full cycle, going back to where it started. Okay, so you can look at any particle. You can look at the particle on the right, in the middle, on the left, any one of them that you want. And each particle is slightly out of phase. What that means is that each particle is doing something different than the particle next to it. Right, so if you pick this particle right here where my mouse is, right, so it's going up, it hits down after the particle on the right hits the bottom. But it hits the bottom quicker than the particle on the left hits the bottom. So it's not exactly moving at the same rate as the particles next to it, but that shouldn't be happening anyways if it's a wave. Now, how does the wave appear to be moving? Well, let's watch this particle as it hits the top. Now, follow my mouse. Do you notice all of these particles are hitting the top? So what that means is the crest of the wave is moving from right to left. And so the wave looks like it's moving left. All right. Now, consider the following snapshot. Okay, so this is a series of masses on a spring. And now if you extend that mass on a spring and you let it go, it's going to oscillate up and down. This is a snapshot of them at one point in time. Okay, so this spring, or the mass on the spring, is oscillating like you see on the right. Now, each one of those is out of phase, but there are some of them that are in phase with each other. In order for two objects to be in phase, they have to be at the same point in their wave pattern. I'm going to switch to the page here for a moment and show you what I mean by that. Okay, so if I have a wave, so here's y and here's x. All right, so let's say I pick a point on the wave, and let's say the wave is traveling from left to right. Okay, so let's pick, I don't want to pick the same point as in the next example. Let's pick this point right here. Okay, so if this wave is moving from left to right, what does that point want to do? Well, imagine this whole thing shifts to the right a little bit. Where will that point be? Well, it's going to be right here at a later point in time. It's going to be a little bit up. So it's going to move up relative to where it is now. Right? So that's its next position. Whichever way the wave is going, to figure out what the particle is going to do next, look at what's coming just before it. Okay, so just before it, it has a higher y value. So this thing is actually going to go up. It's not moving left, it's moving up. And then it's going to move up a little bit more and then down, 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 and then down again. And the cycle will repeat. So what other part of this wave is in the same phase? Is it in the same cycle? Well, if you look at this point right here, it's at the same y value, but that point is not in the same phase. right? Because if we consider this point, I'll actually draw it with a solid circle. If you consider this point, the point that comes immediately before it is lower. So when the wave travels from left to right, this point's actually going to move down, not up. So we said this one's going to move up. This one's going to move down, right? So it's not just about the location, it's about its behavior, what it's going to do, right? So this one has the right location, but the wrong behavior. But if we pick the next point right here, guess what? If this wave moves from left to right, the part immediately before it is right here, which means when the wave moves, this particle is going to move up. So this particle, these two, I'll color them in, these two are in the same y position and they have the same direction and same tendency. So these two are in phase. All right. I don't want to get into more right now. We'll talk more about how to label the various parts of the wave soon. Let's go back to the slides. Okay, so here we have our x and y directions. Now at every x position, we have a different y value. So if we pick these two randomly, so x1 and x2, we can see that x1 has a y value of 0. It's on the equilibrium line, but x2 is displaced in the positive direction. Okay, so they have different displacements. Now, how do we know that they are a quarter cycle out of phase? Okay, so kind of like what we talked about before. Depending on which way this wave is moving, let's just assume for now that it's moving left to right. Although, bear in mind, we don't know that because there's nothing here telling us which way the wave is going. It could just as easily be moving right to left. But whether you decide the wave is moving left to right or right to left, you're going to get the same answer, that they are a quarter cycle out of phase. Okay, let's assume it's moving left to right for now. If the wave is moving left to right, that means the next position for the particle in x1 is to move down, okay? Move down right here. So exactly where the particle on the left is right now. It has to move to that y position, but keep at the same x position, right? So it's going to go down. If you look at x2, x2 is also going to move down. However, it's at a different location. Right now, x2 is at its maximum y value, and it's moving down. x1 is at its equilibrium y value, and it's moving down. So while they have the same tendency, they're not in the same location. Okay, so now how do we know that they are a quarter cycle out of phase? We know that they're out of phase, but how do we know it's a quarter cycle? Well, in order to answer that, we have to understand what it means to have a cycle. Okay, so I'm going to go ahead and draw a series of waves again. So draw a couple here, kind of like that. Now, when we say a wave, or we say a cycle, or even it can be just called a wavelength, these things are the same. Okay, so a cycle means, well, how long is one wave? A wave is, well, distance or the length of something in order for the pattern to repeat itself. So if we start here, we have a crest, we have a trough, and then we have a crest again, and then again a trough, and then again a crest and a trough. So it looks like this is one unique pattern. Okay, so one crest and one trough. Because again, like I said, after that point, the pattern repeats itself. We have a crest and we have a trough. Okay, so there's another wave. And then we have a crest, and here we have half a trough, so we have 1.5 wavelengths. All right, so what does this mean to have something a quarter cycle out of phase? Well, let's say, and let me use some colors here so you can see what I'm doing. If I pick this crest and this crest, okay, these crests are both, if the wave is moving from left to right, both of these points, their next position is to move down a little, right? Where this point is. And so they're both going to move down. These 2 points are in phase. Okay? They're perfectly in phase. These 2 troughs are perfectly in phase. These 2 points right here are perfectly in phase. Now, 2 things that are out of phase, well, if I take my trough, okay, my crest and my trough are half a cycle out of phase. Okay, so the crest and the trough are half a cycle out of phase. Okay, the reason for that is from the location of the trough, it will take half a cycle for it to get back in phase with the crest. Okay, so that's all it means. But keep in mind that this crest up here is half a cycle out of phase with this trough. It's also half a cycle out of phase with this trough, and it's also half a cycle out of phase with this trough. It doesn't matter which one you pick, because after another half a cycle, it's going to be a crest again. It's going to be in the same position and same direction of motion as it is in the beginning. Okay, so crests and troughs are always half a cycle out of phase. The crests and the crests are in phase. So crests are in phase with other crests. The only thing you have to be careful of when you don't pick just crests or troughs, like for example, these two troughs are in phase, these two troughs are in phase, these two troughs are in phase. When you pick any other point, you can't just pick it with the same y value next to it. So looking at this, right, we said that these 2 points were in phase, right? So this one and this one, but this one wasn't, right? Notice they all had the same y value, but only these ones were at the same y value with the same tendency of moving up. So with other points, you got to be a bit more careful, right? So for example, if I pick this point right here, this random point, even though this one has the same y value, this one is going to want to move up after. This one is going to want to move down. Where's the next point with the same y value that wants to move down? Right here. So these 2 points are also in phase, random points. Okay, and then the next point that would happen is right here. And I can keep going on and on and on. All right, so based on the slide we were just on, we were looking at things that are a quarter cycle out of phase. Well, if I have a crest, if I have my crest, if this is a half cycle out of phase and this whole thing is one cycle, then that means if you break this up into 4 pieces, so if I break it here and I break it here and I break it here, okay, so half a crest is a quarter cycle, another half a crest is a quarter cycle, half the trough is the other quarter cycle, and the last half of the trough is the last quarter cycle. Okay, so you just have to pick 2 points that are off by this amount of spacing. That would be a quarter cycle out of phase. So if I was to pick that crest with this location right here, these 2 points are a quarter cycle out of phase. So quarter cycle out of phase. If I pick this orange point and this green point, they are also a quarter cycle out of phase, just based on where they are and where they're going. Okay, so I hope that makes sense. So here, if we're looking at this picture, again, if we assume the wave is traveling from left to right, the particle here at x1 is going to want to go down, right? So where's the next time that's going to happen? Well, here, notice we have a crest and we have a trough. So this x1 is at the very end and beginning of the next wavelength. We have another crest and another trough, right? So, okay, so now start fresh here. So this would be technically the location of x1 if x1 were in phase with x2 and x2 were located right here. But x2 is located at the top, right? It's not located at the start of the wave, it's located at the top of the crest. Between the start of a wave and the top of the crest, that's a quarter wavelength. Hence, it is a quarter cycle out of phase. Okay, the next quarter comes from when it hits equilibrium again. The third quarter comes from when it hits the bottom, so that box is not here. And the last quarter would be when it goes back to equilibrium. It would be somewhere over here. All right, let's keep going. So this is the system as we saw on the previous slide. Now let's say at some time later, we actually have the system that looks like this. And the question is, well, which way is the wave traveling? Okay, which wave is the wave traveling? Well, let's take a look at this. On the previous slide, we just assumed that it was going from left to right to figure out the phase or out of phase and figure out by how much. Okay, so for that kind of an analysis, it doesn't matter which way the wave is going. But if we actually have to know which way the wave is going, now we have to use this information. All right, so based on where x1 is, and we're even told the mass at x1 has gone lower, and the mass at x2, what does it do? It also goes lower. Okay, so if it goes lower, if they both go lower, that means that the wave has to be traveling from left to right. Okay, so that means that our original analysis was indeed correct. So what you need to take from the slide is, if the particle inherits the motion of the particle immediately before it, so on the left, that means the wave is coming from the left. If the wave is coming from the left, that means it's going right. If x1 happened to copy the behavior of the particle to the right, that means the particle on the right interacted with the wave first. Hence, the wave would have been coming from the right and traveling to the left. All right. If we look at either of these graphs, we can define a few characteristics. Well, we can define something called the equilibrium position. We can define the displacement. I'm going to do all that on the paper because I think it's going to be easier for you to see. Okay, so I'm going to draw a really big wave here. And I'm going to have to extend this. Okay, so that's x and that's y. Of course, there are units with that too. We'll get into the units, but for now, I just want you to pay attention to this. Okay, so we already defined what a wavelength was. A wavelength was the amount of distance for one complete cycle. And it really doesn't matter where you start that. By the way, the definition for wavelength will be on the slides. Just figured I would introduce it to you now. So a wavelength, traditionally, it's defined as the distance between one crest and the next crest. Okay, so that means the cycle is going to repeat itself because after the crest, the wave starts going down on both sides. So this is one wavelength. Now the symbol for wavelength, so let me just write it like this. One wavelength, also known as one, and this funky symbol. This is the Greek letter lambda. And we use lambda for wavelength, always. Okay, so lambda, or the wavelength, we can measure from crest to crest. I can measure from trough to trough, which is not drawn here, but I mean, you can imagine it would be somewhere over here. I can measure it from the start of this wave to the start of this wave, the end of this wave to the end of this wave, or any point to another point exactly in phase next to it. All right, but by definition, usually we measure from wavelength, crest to crest. But again, you don't have to. All right, now the slide that we were just on, it's starting to talk about something called displacement. So I keep saying that this line right here, this is the equilibrium line. So if we're considering this to be a transverse wave, in other words, if the wave is moving from left to right, these particles are getting displaced perpendicular, right, to the direction of the velocity. They're getting displaced up and down. So if the particles were not getting displaced up and down and they were at rest, what would they be doing? Well, they would be hanging out right here along this line, right? So if you're not sending a pulse through a rope, the rope would just exactly follow along the x-axis, hence the equilibrium. All right, so displacement would be how far the particle is from equilibrium. So this particle right here has this displacement from equilibrium. So this would be the S value. Okay, now displacements, because it's a vector, it can be positive and it can be negative, and it can be large and it can be small, right? So you can have a somewhat medium positive displacement, a large negative displacement, or a small positive displacement. Okay, so this is the displacement of the wave. Now displacement varies along the wave. If you look, there is a maximum displacement along the wave. You can have it from the equilibrium line to the crest or the equilibrium line to the trough, whichever you choose. It would be the same magnitude of displacement. Oh, let me use orange here. So this maximum displacement is given a special name. We call that the amplitude. So this is the maximum displacement. And amplitude can be measured from equilibrium to crest or equilibrium to trough. Okay? Let's go back to the slides. All right, so here, now based on the animation, you can see that x1 has a negative displacement and x2 has a positive displacement, neither one of which represents the amplitude because they're just not displaced enough from equilibrium. But the amplitude is the maximum displacement. Okay. Period and wavelength. So we already defined wavelength. I introduced you to the symbol lambda, or this Greek letter, okay, which means wavelength. So wavelength is the distance of a full wave, or the length of a full wave. Now, period just means the time of a full wave, or the time of the cycle. Okay, so let me show you this. The reason I can say that this is the wavelength is because this here is x. Okay, x is a unit of measure, which means distance. Okay, so usually x would be measured in meters. So in fact, I should write it like this, x/m, and y is measured also in meters. Okay, so if I had y here, and I had time measured in seconds, okay, so if I had something like this, now all of a sudden, so time is the length of time. Okay, so unfortunately we can't get away from that word in the definition for one complete cycle. Okay, so this would be the period right here. Okay, let's go back to the slides. All right, now a wave takes a certain amount of time to complete one cycle. It travels through a certain length, which we call the wavelength. Now, there has to be also a speed for the wave. As I said in the beginning, sound travels fastest in denser media. Light is actually the opposite, but like I said, we'll study light in grade 12 mainly. So we have to have a way of figuring out and representing wave speed. So we're going to represent wave speed with v. V was speed, and when you don't have acceleration, speed is equal to distance over time, or lambda over t. The last quantity we're going to look at is frequency. Now, frequency just says how many crests per second pass a given point. Okay, so if you have 2 crests pass a given point, that means you have 2 waves that pass that point. If 5 crests pass, that means you had 5 waves pass. All right, so frequency just means how many waves pass a point every second. The reason that it's usually defined with crests is just so that we're more specific. Now, let me go back to the page here. There is a really handy relationship between frequency and period. So frequency is represented by the letter lowercase f, period is capital T. Now, frequency is the number of cycles per second, okay, that pass a certain point. Period, on the other hand, is the number of seconds per cycle. Okay, so how long does it take for one cycle? And hence why the unit of measurement is seconds. Now, notice between these two, the units are reciprocals of each other, seconds per cycle and cycles per second. That would mean that frequency and period are also reciprocals of each other. Okay, so frequency is simply 1 over capital T. So likewise, if that's the case, that means that period is 1 over frequency. Now looking at that, that would mean the unit for frequency is seconds to the minus 1, or 1 over seconds. But we don't like to say that something has a frequency of 10 seconds to the minus 1. We represent it using an easier notation, a better notation. So instead of saying seconds to the minus 1, we say hertz. Okay, so this is hertz. And that's what it represents, seconds to the minus 1. Okay. Now, this formula, which I wrote on the page and is here on your slides, while that's not in your data booklet, you should remember that. It's very important. All right, practice. A spring is moved in SHM. SHM is simple harmonic motion. Okay, so a spring is moved in simple harmonic motion by the hand as shown. All that means is that the spring is moved in such a way that it has an oscillating pattern of compressions and rarefactions. The hand moves through one complete cycle in 0.25 seconds. A metric ruler is placed beside the waveform. What is the wavelength? All right, so this one we can't do on a sheet of paper because all the information is right there on the slides. But you know how to find a wavelength. A wavelength, now based on a transverse wave, we said that a wavelength you measure from crest to crest, or from trough to trough, or at any point in the wave and the immediate next point that is in phase with it. So with a longitudinal wave, it's similar. I mean, there's a lot of similarities. We're going to be equating crests with compressions and troughs with rarefactions. So in order to have one complete cycle, you should have one full compression and one full rarefaction. Or if you start in the middle of a rarefaction, then you have to have the last half of that rarefaction, the full compression, and the first half of the next rarefaction. So essentially, you need all the elements of a complete cycle until the cycle repeats itself. I think the easiest way to do it would be to start from the beginning of this compression. Okay, so the wavelength. So from the start of this compression to the start of this compression. If we look at the measuring tape, that looks like it's about so this would be 4.567. So 4.7 centimeters. And the only thing you would need to do is then convert that into meters. A lot of problems and graphs in this section are going to have units that are not the units that you need to use when you plug it into the formulas. So you got to make sure you read the units very carefully. Again, whether it's in a question or it's on a graph, and convert it to the correct SI unit. So we have 4.7 centimeters. If you divide that by 100, you get 0.047 meters. Okay, well, what about the period? Well, we're not going to see that by looking at the picture because this is measuring distance. But sure enough, the answer lies right here in the question. We're told that the hand moves through one complete cycle in 0.25 seconds. And by definition, period is the amount of time it takes to move through one complete cycle. Hence, the answer is 0.25 seconds. And finally, what is the wave speed? Since we are not considering acceleration here, wave speed is distance over time. Distance being wavelength and time being period. Okay, so what do we have? We have the distance of 0.047 meters divided by the time of 0.25 seconds, resulting in 0.19 meters per second. All right, so now we're going to be looking at distance and time graphs. All right, so the graph on top, graph 1, we see a distance versus time graph. Pay attention to the units, please, each and every time because they will change. Time is measured in seconds. The distance is measured in millimeters, okay, so not meters. We're going to have to convert that. In graph 2, our vertical axis is distance in millimeters again, but the horizontal is distance in centimeters, so just be careful of that. Now, both of these graphs represent the motion of the same object. We just have to know which graph to use to get the information that we need. So for part A, use the graphs to determine the amplitude of the wave motion. Now, what we saw earlier was that amplitude is the maximum displacement from equilibrium. Both of these waves are evenly centered about the d is equal to 0 mark, which is great, which means that d is equal to 0 is the equilibrium. That means in order to find the amplitude, you can measure from d equals 0 to the top of the crest, or d equals 0 to the bottom of the trough, and then take the magnitude of that value. Okay. Now, both of these, notice they represent the same amplitude, and it should. It doesn't matter which graph you read, it's the same amplitude, which is 4 millimeters. Which when you divide by 1,000, you'll get the answer in meters, 0.0040 meters. So there it is on one graph and there it is on the other. That's one thing that you can extract from either graph, amplitude. B, use the graphs to determine the wavelength. All right, so wavelength is the horizontal distance of travel, not the vertical like the amplitude. So now we're dealing with the independent variable axis or the horizontal axis. Okay, so graph 1 measures time on the horizontal axis. That's not what we're going to need. We're going to need the distance graph, graph 2. All right, so wavelength is the distance or the length of one complete cycle. And I only have one complete cycle here on this graph. So I have a full crest and I have a full trough. And so from start to finish, that measures 2.4 centimeters. Or, dividing that by 100, 0.0240 meters. Okay, part C, use the graphs to determine the period. So period is the length of time needed to complete one cycle. That means we're looking at graph 1 because we are measuring time on the horizontal axis. Now in graph 1, we have two complete cycles, right? Two crests, two troughs. So I'll start from the beginning because it's easier. If you start at t is equal to 0, one full cycle will range 1 full crest, and 1 full trough, leading us to the 0.3 second mark. Since that's already in seconds, I don't need to do any unit conversion. Part D, use the graphs to find the frequency. So from what we saw, frequency is the reciprocal of the period. So if we just found the period to be 0.3 seconds, then the frequency is going to be 1 over that. So 1 over 0.3, if you punch that in your calculator, you're going to get 3.3. And like I showed you before, we're not going to put the unit as seconds to the -1. We call that hertz. Part E, use the graphs to find the wave speed. All right, so wave speed. Speed is distance over time. Distance being the wavelength and time being the period. So the wavelength we said was 2.4 centimeters, which we would have to convert to meters again. And the time was 0.3 seconds, which is already an SI unit. Okay, so 0.024 meters divided by 0.3 seconds, we get 0.080 meters per second. Okay. Practice. Graph 1 shows the variation with time of the displacement y of a traveling wave. Graph 2 shows the variation with distance x along the same wave of its displacement. Again, pay close attention to what the axes measure and their units. So we have y is measured in millimeters for both. On the top graph, graph 1, time is measured in milliseconds. Okay, so if you forgot what milli stands for, check your data booklet prefix list. Milli means times 10 to the -3. That means whatever value we get here, in order to convert it to seconds, I'm going to have to either multiply by 10 to the -3 or divide by 1,000, since these are the same things. Graph 2, we can see that the horizontal axis is measuring distance in centimeters, so that also has to get converted to meters. All right, use the graphs to determine the amplitude and wavelength of the wave motion. If you want to pause the video at this point when we do the practice questions, pause it, give it a try for yourself, and then replay it, and you can see if you're getting the answers correct. Okay, hopefully you had a chance to think about it or you paused the video. Amplitude, remember, we can get from either graph because the vertical axis measures the same thing. Sure enough, the amplitude is the same on both. It is 2.0 millimeters. Okay, so if we convert that to meters, divide that by 1,000. Okay, so we move the decimal place 3 spots to the left since 1,000 has 3 zeros in it. Now the wavelength we would have to get from graph number 2 because this is what's measuring distance. Okay, so if we start here at the beginning, we start off with 1 full trough and then 1 full crest. So we stop here at the 0.3 mark because that's when the next full trough will begin. Okay, so 0.3 centimeters, divide that by 100, and we get 0.0030 meters. B, use the graphs to determine the period and the frequency. Okay, so once again, period we get from graph number 1. If we start from the beginning, we start at the right half of a crest. Okay, so right half of a crest, left half of the trough, right half of the trough, and left half of the crest. So we stop here at the top of the next crest. Okay, so how much time does that take? Well, if we follow this down, okay, so each one of these boxes represents 1/10 of the way from 0.2 to 0.3. So that's going to be increments of 0.01. All right, so we're exactly in the middle. So that's going to be 0.25. The units, milliseconds. So 0.25 milliseconds is the period. But we need to convert that to seconds. So again, we divide by 1,000 and we have this figure right here. Once you have the period, finding the frequency is a simple task. Simply take the reciprocal of the period. Now, because finding frequency is also using a physics formula, whether or not it's in your book, you have to make sure that the numbers you plug into this formula are SI units. So I have seconds, so I plug in the value that has seconds, not the one with milliseconds. Otherwise, I cannot say that the unit here is hertz. Okay, so something to notice is this thing oscillates really fast. Look at that tiny period right there. Okay, so it would oscillate several times a second without you even noticing it. Specifically, it is oscillating 4,000 times every second. C, use the graphs to determine the wave speed. So just like before, speed is distance over time, or in this case, wavelength over period. Okay, so we already have these values in the SI form, 0.0030 meters divided by 0.00025 seconds, leaving us with 12 meters per second. Okay, example. Graph 1 shows the variation with time t of the displacement x of a single particle in the medium, carrying a longitudinal wave in the positive x direction. Okay, part A, use the graph to determine the period and the frequency of the particle's simple harmonic motion. Again, that just means figure out these values for the particle's oscillation. All right, so period, again, it's the amount of time. So if we're starting from the top of a crest, we go back to the top of a crest. That's 0.2 seconds. So at least we don't have to do any unit conversion there. Okay, frequency is the reciprocal of the period. So 1 divided by 0.2, that's 5 hertz. That means it's oscillating 5 times a second. Okay, graph 2 shows the variation of the displacement x with the distance d from the beginning of the wave at a particular instant in time. Okay, notice that x in the vertical is in centimeters, d in the horizontal is in centimeters. Okay, so we're going to determine the wavelength and wave velocity. Wavelength, if we start from the beginning, we have 1 full crest and 1 full trough. So that's 1 full cycle, 16 centimeters or 0.16 meters. For the speed, or the wave velocity, we're going to need displacement over time, or distance over time in this case. Okay, so the distance is the wavelength, so that's 0.160 meters, and the time is the period, which we found on the previous slide, 0.2 seconds. Dividing those two gives us 0.80 meters per second. All right, so we have V is equal to lambda over T. Okay, so this is the first formula we saw. We saw F is equal to 1 over T. And then from those two, we're going to derive the formula on top in blue. Well, very similar to this, just without the C, we're going to put a V. Okay, so if speed is equal to distance over time and frequency is 1 over time, we can take this ratio and split it up. So that is the same as the next line, lambda times 1 over T. Now 1 over T is your frequency, hence we get V is equal to lambda F, or V equals F lambda. This equation right here is called the universal wave equation. Now in your data booklet, if you just pause for a second, so let's go back to the data booklet. So go to your data booklet. In box 4.2, there's a very similar formula, except instead of V equals F lambda, it's C equals F lambda. It's the same formula. C and V both represent wave speeds. The difference is V is a generic symbol for wave speed. When you label it as C, it automatically means the speed of light. A C represents the speed of light, lowercase c. So this is referring specifically to light waves. However, if you replace the lowercase c with the V, it simply becomes the standardized universal wave equation. Okay, so this is the same thing. All right, example. A traveling wave has a wavelength of 2 centimeters and a speed of 75 meters per second. What is its frequency? Okay, so you'll probably notice there's a lot less calculation in this section compared to previous sections that you've done, but there is a lot of conceptual knowledge you have to understand. Example, okay, so we have a wavelength of 2 centimeters, and we have a wave speed of 75 meters per second, and we have to find the frequency. First things first, you have to convert your wavelength to meters, so that's 0.02 meters. Okay, the universal wave equation tells us that V is equal to F lambda. Don't worry about writing this as C equals F lambda first. You can just jump to this formula. Okay, rearranging for frequency, that's going to be V divided by lambda. So that's 75 meters per second divided by 0.02 meters. So the meters cancel, and you're left with seconds to the -1, which is the unit for frequency. But remember that we just write that as hertz. So 75 divided by 0.02, and we get 3750 hertz. So that is the frequency of the traveling wave. Okay. Now, I did say that we will talk about light waves a bit in grade 11, but we're going to save the majority of this discussion for grade 12. So the only things you need to worry about for light waves are what you're going to see in this video. There are some other slides on your PowerPoint slides document that we're not covering in the video, and so what that means is that you don't need to cover it. Okay, they should already be hidden, but if you do see it or you do end up printing it, just make sure you skip it if we are not covering it in the video. Okay, so sound is a wave. Light is also a wave, and sometimes we consider matter waves as well, kind of like the waves in a wave pool. Now, light is only a or visible light is only a very small portion of the electromagnetic spectrum. Okay, so those colors that we see, red, orange, yellow, green, blue, indigo, violet, all of those colors make up the visible spectrum of light, but it's a very narrow range that we can actually see. There are so many more wavelengths and frequencies of radiation. So visible light is a type of radiation. Now, there's radiation that has less energy. Those would be the ones here on the left. So radio, TV, cell phones, microwaves, infrared light. This is heat, by the way. Infrared means heat. And we have radiation that has more energy and is dangerous the higher the energy it goes. Things like ultraviolet light, X-rays, gamma rays. Okay, so ultraviolet, you can't stay in the sun too long because the UV rays are harmful. However, it is those same UV rays that produce the much needed vitamin D in your body. So make sure you go out there for 15 minutes at least a day and get that vitamin D. Now, here's that visible spectrum, that narrow part of the entire electromagnetic spectrum that we can see. When we look at it really closely, we can see that it has light from red all the way to violet. And the red light has a very big wavelength. The violet light has the smallest wavelength. And so that tells us that violet bluish light has more energy than red light. You're going to notice the unit of measure is nanometers. On your formula booklet, nano is the prefix, which means times 10 to the minus 9. Again, we're not going to worry about this too much. We're not going to worry about the specifics of light in grade 11 physics, but we're going to do some simple problems, which you'll see some examples of over the next couple of slides. Okay, couple things before we get to that example. With light, so I showed you on the formula booklet that the formula in box 4.2 says C equals F lambda instead of V equals F lambda. And the reason for that was because lowercase c represents the speed of light. Now, whether you're talking about infrared radiation, X-rays, microwaves, gamma rays, or visible light, any color of the visible light, all of it travels at the same speed, the speed of light. And that's 3 times 10 to the 8, or 300 million meters a second. Okay, so this is how fast light travels in a vacuum. In other words, when it's not traveling through a medium. Okay, so contrary and different than sound, while it travels faster in denser media, light travels faster in less dense media. And a vacuum, by definition, has no particles in it, so it will travel the fastest there. It is because of this incredibly high speed that you don't notice the light moving when you turn on the light in a room. It seems to be instantaneous, but it's not. It's moving. It's just moving at 300 million meters a second. All right. So there's that formula that's in your data booklet. All right, the wavelength of a particular hue of blue light is 475 nanometers. What is its frequency? So let's go to our page here. Okay, so the wavelength is 475 nanometers, and we want to know the frequency. At first glance, it looks like not enough information has been given to us in this question, but we actually have been given enough information. Just like in a projectile motion question, you won't be told that the acceleration due to gravity is 9.81, but you know that you have to include that for the y direction. Here, you're not told that the speed of the wave is c, and that is 3.00 times 10 to the 8 meters per second. Now, you don't have to memorize that. So if you take your data booklet and we go to our equation of our page of constants, okay, so there's the acceleration due to gravity, 9.81, the first one. Speed of light, well, it's about halfway down. Okay, So speed of light in vacuum, it's represented by the letter lowercase c, 3.00 times 10 to the 8 meters per second. So it's right there in case you ever forget. Okay, universal wave equation, V equals F lambda, or in this case, C equals F lambda. So if we rearrange for F, it's going to be C over lambda. So that's 3.00 times 10 to the 8 meters per second divided by, now, nanometer. Okay, so I'll show you where that is in the data booklet in case you forgot. So we're looking at metric multipliers, the prefix. So nano is right here. Nano means times 10 to the minus 9. Okay, so whatever number you have, take out the n and replace it with times 10 to the minus 9. So 475 times 10 to the minus 9 meters. So this way meters cancel with meters. You're left with seconds to the minus 1, which is what you want. So here we go. 300 times 10 to the 8. Oh, sorry. 3 times 10 to the 8 divided by 475 times 10 to the minus 9. So that's 6.32 times 10 to the 14 hertz. All right, so the frequency of the blue hue is 6.32 times 10 to the 14 hertz. All right. Here we go. The graph shows one complete oscillation of a particular frequency of light. Part A, what is its frequency and what part of the spectrum is it from? And so obviously you don't have to memorize the wavelengths in the different parts of the spectrum. It would just be understood that you would be able to look it up if this question is asked. All right, so what's the frequency? Well, to find the frequency, I can find that from the period, right? So the length of time for one cycle. And I can see in this picture, I'm given exactly one cycle. And it takes 6.0 times 10 to the minus 16 seconds. So again, we got to be really careful with the units there. It's seconds, but it's times 10 to the minus 16 seconds. So example. All right, we're looking for frequency, and I think we're saying the period here is 6.0 times 10 to the minus 16 seconds. Okay, so that's easy. Frequency is the reciprocal of period, so that's 1 over 6.0 times 10 to the minus 16 seconds. Oh, there we go. What is that? 1.7, let's call that, times 10 to the 15. All right, so 1.7 times 10 to the 15 hertz. Let's see what part of the spectrum that is from. Okay, so if we look at our electromagnetic spectrum here on the top, so we had something on the order of 10 to the 15, so that's right here. If you notice, you have a low frequency here, 10 to the 4. That's about 10,000 hertz. And up here you have 10 to the 18. I'm not even going to try to guess what that prefix is. 10 to the 15 is right around here. So we're in the UV ultraviolet region. Part B, what is the wavelength of this light wave? Well, if we want to know the wavelength, we know c, the speed of light, and we just found the frequency. So that's not going to be too difficult. So let's go to our page. So this was Part A. Part B, wavelength is question mark, c is equal to f lambda. So lambda is c over f. So that's 3.00 times 10 to the 8 divided by, and that's meters per second, divided by 1.7 times 10 to the 15, also seconds to the minus 1, since that's hertz. Okay. So that means these two units cancel, and we're left with meters, which is what we want. So 3 times 10 to the 8 divided by 1.7 times 10 to the 15. 1.8 times 10 to the minus 7. And that's meters. Now, a lot of times, when we study this in grade 12 physics, you'll see this more, but you probably noticed that a lot of the light waves were given in something called nanometers. Nano is times 10 to the minus 9. I'm just going to show you this really quickly. It is optional, so if you want to just tune this part out, that's fine, but it's still good practice for you. If we want to write this as something times 10 to the minus 9, I would have to imagine this. What this right now means in scientific notation is that wherever the decimal is, the true number, I would take this decimal and move it 7 places to the left. 7 because of the exponent and left because of the minus sign. So if this was times 10 to the minus 9, that means that I have to move the decimal to the left 9 spaces, 2 extra spaces. So to compensate for that, I can't put 1.8, I have to put 180 because now the decimal would be here. And so in order to get it to between the 1 and the 8, I have to move it an additional 2 spots to the left. Okay, so 180 times 10 to the minus 9, or 180 nanometers. So either one of those is fine. Okay, back here. Oh, sorry, it took a while for it to pop up there. Part C, determine whether or not this light is in the visible spectrum. Okay, so that just has to do with you knowing how the spectrum looks, having access to one, so you can see the various range of wavelengths present. So we just determined that it's 180 nanometers. Okay, the visible spectrum is from about 400 to 700 nanometers. That means it is much smaller than violet light. Okay, so that's a pretty high energy light right there. That's ultraviolet. All right, this is our last slide. Some of you, well, since this may be your first time learning about sound, if not, you may have seen this demonstration in chemistry. It's something called the bell jar demonstration. So all it is this. Inside of this jar, you have a bell, a buzzer, and it's making a lot of noise, which you can easily hear. Now notice that with this jar, there's a little funnel here on the outside. And generally what happens is the air inside of this gets extracted. And the more air that comes out, the less sound that you can hear. Remember that sound requires a medium to travel. If there are no particles to transfer the energy from the location of sound creation to where you are, you're not going to hear anything. And so theoretically, if you have a vacuum in here, which is the absence of any sort of particles, there should not be able to be any sound traveling at all. Okay, so everything that I'm explaining is here on the slides. But the idea is the longer that the pump takes the air out, the less and less sound you can hear until the point where all the air has been sucked out and you can't hear the buzzer at all. So that's pretty scary. Of course, if you were ever trapped in a room with no air particles, I think your biggest worry is that you have no oxygen, not that no one can hear you scream. So there's that. With that gruesome and slightly disturbing example aside, that last point here on the slide is that the demonstration also shows that light can still propagate through a vacuum. Don't worry about answering that question. We will answer it in grade 12 physics. Otherwise, that is it for this video 4.2.